Hi, we are engineering brothers, and once again we have got our another interesting problem over here, which is our torque and analogy additional problem 3. And you can see that up to this one, for both our torque voltage and torque and analogy, the mechanical differential equation are identical over here. That is why I should have started from these two differential equation over here, and quite naturally the first differential equation is this one and the second differential equation will be this one. Now the next stage will be quite naturally the simpler one. Just by looking at this table, I am just going to replace this parameter over here. So let us just go for that one over here. So the torque is replaced with our current over here, as we are focusing on our torque current analogy over here. So the torque is been replaced with our current over here. So this is our IT for our equation 1. The G1 will be replaced with the moment of inertia, that is replaced with our capacitance C1. So this one will be C1 D2. The angular displacement will be replaced with our flux. So this one will be D2 phi t divided by our DT2 plus B12 will be the damping coefficient will be replaced with our 1 by R. So this one will be 1 by R12 d dt of the theta t is quite naturally our flux linkage over here. So this one will be our phi t minus of our phi 1 t plus once again the k. The k is quite naturally replaced with our 1 by L. So this one will be 1 by L, and the theta t, the angular velocity, or sorry, the angular displacement, that is replaced with our flux. The same one that I have repeatedly done over here. So this one is phi t and this one will be our phi 1 t. So this will be our first electrical equation according to our torque current analogy over here. I have just utilized or used this chart for our torque current analogy over here. So the torque is replaced with our current I, the moment of inertia that is replaced with our J1, that is replaced with our capacitor C1, and at the place of our theta t, angular displacement, I have replaced that with our phi. So this one is phi. Similarly, for our B12, we have got the damping coefficient that is replaced with our 1 by R. So this one will be 1 by R12 ddt of, and so the angular displacement that is replaced with our flux linkage. So this one will be phi t and this one will be minus of phi 1 t. So at the place of our theta t, I have utilized or used our phi t. And similarly for our stiffness, we have got the 1 by L. So that is replaced with the 1 by L, and inside our bracket I do have the angular displacement that is replaced with our flux linkage. So this one will be phi t minus of phi 1 t. So this is our first electrical equation over here. Similarly, for our next equation, we are going to utilize the same procedure over here. The B is replaced with our 1 by R. So this one will be our 1 by R d dt of the angular displacement that is replaced with our flux linkage. So this one will be our phi 1 t plus the J2 or moment of inertia that is replaced with our capacitance. So this one will be our 1 by C2 D2, the angular displacement that is replaced with our flux linkage phi 1 t divided by our dt2 plus the B12 that is replaced with our 1 by R. So this one will be 1 by R12 dt of our I think the equation do have the error over here, because the B12, as the B12 is the common factor over here, so quite naturally if you do take the theta 1t as your common factor over here, so this one should be our theta 1t minus of our theta t. Okay, now let us do complete our replacement of our parameters over here. So inside our bracket I do have d dt of our theta 1t. At the place of angular displacement I am just going to utilize the flux linkage over here, so this one will be our phi 1t minus theta t. Theta t means our phi t, this one. And quite naturally for our k we have got plus, the k is replaced with our 1 by L, so this one will be our 1 by L, and inside our bracket I do have the angular displacement that is replaced with our flux linkage, so this one will be our phi 1t minus of phi t, that is equal to 0. So this is our second electrical equation over here. I just do require to check over here once again if you have considered our present consideration over here. So this one will be our j1 d2 theta t divided by dt2. This one is absolutely correct. Then b12 is placed in between our middle part over here, so b1t means d dt of theta t minus of theta 1t plus our k theta t minus of theta 1t. So this one is our correct answer portion over there. And in our next equation we do have the b d theta 1 by dt plus of our j2 d2 theta 1t divided by dt2 plus b12 is the common factor in between our two displacement, angular displacement part over here. Because of that one, d dt of theta 1t minus of theta t plus of our k theta 1t minus of theta t, which is equal to 0. So I have just replaced that with our table parameters over here, just like our previous two problems for our torque current analogies over there. So just using this table for our torque current analogy, I have interchanged the parameter just by looking at this given analogous chart in between our mechanical and electrical parameters over there. And after that I have got these two equations of electrical 1e and 2e over here. And what is going to be the next step? The next step will be just by looking at these two equations. I think we do require to further modify our equation over here. So to do that we do utilize the analogous parameters of angular displacement over here. So analogous parameters means this is equal with our both our mechanical and electrical parameters over here, and I have taken the angular displacement factor over here, which is our theta t. So the angular displacement theta t, that is analogous with our phi t over here, which is flux. Now if you do take the common, or sorry, if you do take the derivative on both sides with respect to time, so d dt of phi t, so this one is d dt of our phi t. This one should be our theta t, as we are taking the derivative on both sides over here. And as the analogous concepts are quite considered, so for our left hand side we have considered that one will be our mechanical part over here. So this one will be d dt of theta t, that is quite natural, d dt of phi t. And according to the definition for our electrical systems, we do know that the rate of change of flux with respect to time actually do lead us to the consideration for our voltage over here. So this one will be our et. Okay, and quite naturally we do require to find out the exact expression for flux, because we need to replace that flux element over here. So according to the relation we have got that as we have already utilized the mechanical equations over here, so we no longer do require these two equations over here. So I just erase this portion, as just by looking at this analogous concept or looking at this table for our torque current analogy, we have replaced our mechanical equation into electrical one over here. And after that these two equations are absolutely intact over here, and the first relation is d phi t by dt, which is equal to et. Now with the help of this expression we have got d phi t dt, that is actually our, that is the exact definition for a voltage, which is et. Now with the expression or with the help of this relation we have got d phi t, which is equal to et dt. Now if you take the integration of both sides, we have got integration of d phi by t, that is ultimately lead us to the expression as integration of et dt. So what is the exact definition for that one? Integration of d phi by t, phi t, that actually leads us to the expression as phi t is equal to our integration of our et dt. Now, just by utilizing these two relations, the first one is d phi by dt is equal to et. So I'm just going to write down over here. The first relation is our d phi t by dt, that is actually our et, that is our first relation, and our second relation will be quite naturally our phi t, which is equal to our integration of our et dt. So this is our second relation. Now in our next step we are going to replace these two relations on this equation 1e and 2e, and after that we do require to form the circuit diagram for that consideration over here. So just wait for my next part. If you like my video, so what are you waiting for? Please do subscribe my channel, hit the bell icon for more updates, and stay tuned to the channel. Thank you and goodbye.